Hello everyone, welcome back to your research buddy, and in this video we will talk about the position of Fermi level as we have discussed in previous video about the Fermi Dirac distribution and Fermi energy. Okay, so before starting with the position of Fermi level, let's have a basic idea about semiconductors. So as we know that semiconductors are of two types. Alright, so semiconductors are of two types. One is intrinsic type of semiconductor and another one is extrinsic semiconductor. In case of intrinsic semiconductors are pure semiconductor. Alright, and these are free from any impurity, right? Okay, so intrinsic type of semiconductors are free from any impurities, but extrinsic type of semiconductors are only prepared when we dope something within pure semiconductor. It means these are the doped or impure semiconductors, right? And these type of impurities we are putting if, and there are two types of impurities we can put in a pure semiconductor, or during our doping. If we put pentavalent impurities, then that is formation of another type of semiconductor which is N type, and there is P type. It means we have two types of extrinsic semiconductor. We have two types of semiconductor, and then one is intrinsic, these are the pure form, and then extrinsic type of semiconductors are further of two types. One is N type and P type. In case of N type semiconductor, we have majority carriers are electrons, and in case of P type we have holes, majority carriers, right? Okay, so I hope you have some basic idea about these type of materials categorized under semiconductor. Okay, now let's talk about the position. What we need to find out the position, and this is important topic, position of Fermi level in intrinsic semiconductors. Okay, so in case of intrinsic semiconductor, what we need to find out is the position of Fermi level. Okay, so let's start with the concentration. Okay, so I'm going to start with the concentration of electrons in conduction band. Okay, conduction band. So Ne, which is representing the concentration of electrons, so Ne, which is equals to 2 into 2 pi Me, here I am taking star, kT over h square, and there is 3 by 2. Okay, and also exponential minus into Ec minus Ef over kT, right? So this is the concentration of electrons in conduction band, and in case of concentration of holes in valence band, so this concentration represented by NH is equals to 2 into 2 pi mass of hole. Okay, and going to take star here. We will define all these parameters. First of all, what we need to do is to write this equation 3 by 2 again, exponential minus Ef minus Ev divided by kT. All right, so here let's define all these parameters. So here what we are using, Me star, which is representing the effective mass of electron, okay, or electrons, and then Mh is equals to effective mass of holes. Here Ec representing the energy of conduction band, and we have EF, which is representing Fermi energy. Also EV is equals to energy of valence band. All right, now in okay, so in these equations what we are going to take, we are going to take NC. So NC we are going to represent with this term, which is 2 pi me star kt over h square to 3 by 2, which is representing NC, and NB is equals to again 2 pi mh kt over h square 3 by 2. Okay, so by using this equation number 2 in these equations under equation number 1, and this equation is representing the effective density of electrons in conduction band, and this is representing effective density of holes in valence band. All right, now we know that in intrinsic semiconductor, electrons and holes concentration is equal. Okay, so in case of intrinsic semiconductor, electron and holes having same concentration, and electron hole pairs can generated because of thermal effect. Okay, so there is the formation of electron and hole pair due to thermal effect. So we can write that Ne is equals to NH. All right, so we are equating these two equations. Also by using this equation number 2, what we are getting, so we can write by using these equation number 2 in equation number 1, NC exponential EC minus EF minus outside KT is equals to NB exponential EF minus EB over KT. All right, okay, so we can write this equation as NC over NB is equals to exponential minus EF minus EB over KT, right, divided by exponential minus EC minus EF over KT. All right, and by taking this upside, exponential EC plus EB minus 2EF over KT, and this is equals to NC over NB. Now take log on both sides. By taking logarithm, ln NC over NB is equals to, this exponential is going to be cancelled out with logarithmic, so EC plus EB minus 2EF divided by KT. All right, so okay, so if effective mass of electron is equals to effective mass of holes, as we know that hole is nothing but the vacancy, the void of electron, so can we take these two equal, and also NC is equals to NB as we have intrinsic semiconductor. Okay, so this property will be there. Then by using this identity in above equation, what we are getting, so we got this will become 0, then we are getting 0 is equals to EC plus EB minus 2EF. all right, and by taking this you can have KT here, and then KT going to be that side will become 0 again. So we have left with EF is equals to EC plus EB over 2, and we know that if this is conduction band and there is a valence band and there is conduction band, then the distance between these two is represented by band gap Eg. So we have Eb is equals to Eg by 2, which is we can write that Ef is equals to Eg by 2, half of the band gap. It means what will be the position of Fermi level? So Fermi level found if this is valence band and there is conduction band, then Fermi level is at the half of the valence band and conduction band. So this is the position of EF, and this complete from here to here is EG, and we got a situation when EF is equals to EG by 2. So this is for intrinsic type of semiconductor. All right. And in case of extrinsic semiconductor, for extrinsic semiconductor and generally for N type, we have valence band and we have conduction band. Okay, so due to majority of electrons present here, there are number of electrons are there which got excited. Okay, and the position of Fermi level is now shifted towards the lower of conduction band. So this will be the position of EF in case of N type semiconductor, and in case of P type semiconductor we have a P type semiconductor. Okay, so valence band, conduction band. Due to vacancy of electrons, there is a number of vacant electrons are there. So we got the position of Fermi level is close to this valence band. Okay, so these are the positions of Fermi level. We have derived a complete derivation for intrinsic, and then we have also discussed about extrinsic position of extrinsic semiconductor. All right, so this is all about this video. If you have any question, you can comment below. Thanks for watching this video. I hope you like it. I'll see you in the next one. Thank you.